All right, let's go ahead and do our sound check. I can hear myself. Do I see footage from my document camera? Can I see everything moving? Are we all good there? Looks like it. Okay, then I guess we are ready to go. Let's do the usual routine. Put away the headphones first. I would keep them on, but they tend to hurt my ears, and it's not like there's anything I have to listen for, so not worth it. Not when I'm going to be here for probably 3 hours or so. Okay, so our topic for today, we are starting a new chapter or new unit, whatever you want to call it. I don't particularly care. We're starting a new topic, which isn't really going to involve a lot of new stuff. If you've been paying close attention and practicing enough with kinematics, then this next topic should be pretty easy to grasp. We already have all the equations and formulas we need, everything we learned about vectors and everything we learned about kinematics. We're just going to put all of that together in this chapter to analyze two-dimensional motion, also known as projectile motion. So that'll be our topic for the day. Last time we wrapped up with a problem, as you can see here, with my poorly drawn horse and some sort of stuntman. The stuntman was moving vertically, the horse was moving horizontally, and we had to get the horizontal and vertical motion to line up just perfectly so that the stuntman lands on the horse as it passes under him. And we're not going to do anything that's too different from that here. With projectile motion, the major difference between this situation and projectile motion is just going to be that we're dealing with one single object that's doing both the horizontal and vertical motion at the same time. So that is our new topic, projectile motion. I guess I'll start it over here. Gotta use the whole paper. Projectile motion. Now, technically, we could go into like the broader topic of two-dimensional motion. We will see another type of two-dimensional motion in a later chapter, circular motion to be specific. But most of the time we're just going to be dealing with projectile motion situations, which are situations that have vertical motion subject to the acceleration due to gravity, along with horizontal motion, which will usually not have any acceleration associated with it, though we can talk about how to deal with those scenarios where there is some sort of horizontal acceleration. We will see a couple of examples where the horizontal velocity is subject to change. So let's go ahead and put together what we need as far as equations are concerned. First, let me draw the scenario. So our scenario is going to look like this. Our basic scenario, the most basic projectile motion problem, looks like this. An object gets fired from ground level at some angle, we will call it theta, and it will have some initial speed, v initial, and it will go into the air, traveling both vertically and horizontally. So this time when I draw these wide parabolic arcs, they are to be taken literally, unlike what we were doing for free fall, where I was only drawing them as wide arcs so that my illustration had enough space for me to write things around it. And yeah, so this is a scenario where the acceleration is primarily going to be due to gravity. We're usually not going to have any sort of horizontal acceleration. And the effect of that acceleration is going to be not only a change in magnitude, as we usually saw with one-dimensional kinematics, but also a change in direction. And that change in direction happens in 2 dimensions rather than 1. Back in the previous chapter, whenever we had a change in direction, it was only a reversal of direction. If you had something moving forward but accelerating backward, then we would say it slows down first and then it comes to a stop and then it starts accelerating in the opposite direction. But that was the only direction change we would encounter, if any at all. It would just be a complete 180. So that happened whenever the direction of the acceleration was exactly opposite to the direction of the velocity. Let me go ahead and draw it actually. When your velocity was exactly opposite, what color do I want for this? Let's do green. When your velocity was exactly opposite to your acceleration, when they were 180 degrees apart in terms of their direction. The scenario we encountered more often was when the velocity and acceleration were at 0 degrees to each other, when they were in the same direction, when velocity was one way and acceleration was in that same direction. So again, acceleration, velocity, and in this case the angle between them would be, well, they're in the same direction. There is no angle between them. This would be a 0 degree angle in between them. And now we have the acceleration for this object is going to be just the acceleration due to gravity, which is straight down. And as you can see, right from the beginning, the acceleration due to gravity, acceleration equals negative g, is neither at 0 degrees nor is it at 180 degrees. It's at some other angle. And that's going to have 2 effects. If the acceleration is anything other than 180 or 0 degrees, you are guaranteed to be changing the direction of your velocity as time passes. In these 2 scenarios from the previous chapter, you could change the magnitude of the velocity without a change in direction. In the 180 degree scenario, a change in direction would only happen after the velocity had been brought all the way to a magnitude of 0. But over here, the change in direction is guaranteed at all times, so long as the angle between the acceleration and the direction of the velocity is something between 0 and 180. So that's our first notable difference. And we're also going to see, along with this change in direction, we're also going to see a change in magnitude. There will be one specific scenario, one specific moment in time where the object will accelerate by having only a change in direction without a change in magnitude, and that'll be right up here. So the way that this velocity changes, at this point it's this. Let's say at this point it'll be something like this. At this point it'll be straight to the right. At this point it'll basically mirror what we saw there. And I'm not drawing these to scale, am I? Yeah, I should have drawn that one a lot shorter. And then I guess at this point it would be basically the opposite of that. Yeah, we're still going to see some symmetry going on here, at least for this very classic projectile motion case. So when you're right here, your acceleration, at all of these points, the acceleration is still straight down. It's still just negative g. But only at this point right here, will the acceleration cause no change in magnitude, only at that point. Everywhere else, on the way up, the overall magnitude is going to decrease, and on the way down, the overall magnitude is going to increase. But right up here, for that split second, the only thing that acceleration will do to the object at this point is cause a change in direction only. And we can go over the vector addition and illustrate why that's going to be the case. So I guess what I want to state here is, just to complete these scenarios, the third special case, if that's what you want to call it, is when velocity and acceleration are at 90 degrees to each other. When velocity and acceleration are at exactly 90 degrees to each other. So 0, 180, and 90 degrees are all kind of special cases. In all other cases, for all other angles between acceleration and velocity, you're going to see velocity changing in both magnitude and direction. But for these three special cases, you'll see only one change, typically. With the 180, we already talked about, you can get a change in direction, but only after the magnitude has been brought all the way down to 0. Okay, so those three cases have been listed. This case will become more important in a future chapter when we talk about circular motion. Some of you might already be able to figure out why. But I want to go ahead and elaborate now on why the acceleration would cause a change in direction only for this case, and then we'll talk about why it causes a decrease in magnitude as you go up and an increase in magnitude as you go down here. So let's go ahead and do that. I want to do, let's see, how do I want to do this? I guess I want to change colors first of all. Let's say I have an initial velocity that looks like this. And I've got my acceleration, which is straight down. I guess I'll keep green for this. We know that a change in velocity occurs when the acceleration acts on the object for a certain amount of time. So we say acceleration times time is equal to a change in velocity. Or in other words, if you look at our first equation of kinematics, actually not even that, our definition of acceleration is change in velocity over change in time. Usually we just call the change in time just t. And so our acceleration can be rewritten as v final minus v initial over t. And I'll use the vector arrowheads here. We can go back to that. Okay, so if this is my v initial over here, and I multiply the acceleration by some amount of time, then I get something called AT. I get some sort of AT, which will be in the same direction as A because t is a positive scalar usually. So let's say, I don't know, after 10, maybe not 10, maybe after 3 seconds, you get an AT equals, let's say we get an AT that looks like this. Same direction as A, just greater in length. Or it could be smaller than length if t is like a small fraction. It doesn't have to be necessarily an increase in length. But yeah, this AT is equal to a change in velocity. And if we add the change in velocity to the initial velocity, we get the final velocity. That's kind of the definition. Change in velocity equals final velocity minus initial velocity. So if I add initial velocity to my change in velocity, then I can get the final velocity. Well, this is a vector, and this change in velocity is also a vector. And I can just do tail to tip addition here. So if I take this and I add it tail to tip to this, maybe I should draw another copy of it. Let's draw another copy of v initial over here. So there's v initial, and then plus delta v, which is going to look like that. Then the sum of those two vectors is just connect the last exposed tail to the last exposed tip. I didn't mean for this to look like a 90-degree triangle, but I guess that's what it ended up looking like. That was unintentional. But yeah, this would be v final. Okay, so where's the change in magnitude coming from? The change in direction, I mean, we can see that pretty obviously. But where's the change in magnitude coming from? Well, if I were to do what I did in the unit 0 when we did vector decomposition, one way I could deal with this is I could take v initial, I could figure out what angle theta v initial was at, and I could break v initial into two components using sines and cosines. So v initial times sine of theta would be this upward part of v initial. I guess I'll call it vy initial. And then that doesn't look like a good I, but oh well. And then I could take the horizontal component and I could call that, where do I don't even have the space to write this in. I'll just like squiggly arrow to it. We'll call that Vx initial, the x component of the initial velocity. And you can see the delta v is completely vertical. So delta v can just add, or in this case, since they're in opposite directions, directly subtract from vy initial, and you'll get a change in magnitude. And in this case, since delta v is bigger, you'll also get a change in direction. But at the very least, a change in magnitude for the y component of the velocity, while the x component of the velocity doesn't change. Okay, so how does that affect this final velocity's magnitude? Well, the final velocity is going to be, where do I want to write this? I guess I'll write it down here. The magnitude of the final velocity is just going to be, if we do Pythagorean theorem, it's going to be the square root of the y component of the final velocity squared plus the x component squared. I probably should have written the x component first, because that's how we usually write it. X's before y's before z's. The x component final is the same as x component initial. It didn't change. I didn't add or subtract anything from the horizontal part of the motion, but the vertical part of the motion is changing because of gravity. So if this part is changing, then the overall magnitude of v final must be changing. And that's how we know we're experiencing a change in magnitude. If the angle between acceleration and initial velocity is not 90 degrees. If the angle is 90 degrees, then we don't experience a change in magnitude necessarily. Well, I mean, over time we will. Let me flip over to another page and let's talk about the 90-degree scenario. So if I have, let's draw another scenario. Let's say I have initial velocity like this, and let's say I have an acceleration like this, completely perpendicular to it. Let's say I did this for a short amount of time. Let's say that I get a delta V. Let's say I get delta V equals AT. Let's say that's some tiny amount like this. And let's say I want to add that to my V initial. So if I draw tail to tip addition V initial plus delta V wrong color, equals V final, and I forgot to write down delta V on that vector, so that'll be V final, and I'm forgetting my arrowheads too. I mean, at this point it's kind of just arguing semantics. Yeah, there we go. So if I do V initial plus delta V, I get this V final, which looks to be about the same length as V initial. If you do it for a small enough time, you actually will get just a change in direction without a change in magnitude, and you can easily see how that's possible if you try to look at the components of V initial. V initial has components of, well, nothing in the vertical plus something in the horizontal direction, and your acceleration gives you a change in velocity only in the vertical direction. So your delta V doesn't directly add or subtract. It doesn't directly add to or subtract from your initial velocity's magnitude. It will over time, because you go from having no vertical component over time. Your V final, you go from originally having no vertical component, so this part is unchanged, horizontal component is unchanged, and vertical component is initially 0, but you eventually go towards having a vertical component. Some non-zero vertical component, and then you do experience an increase in magnitude. But if this object has its velocity turn around, I guess I should probably be saving this for when we get to the circular motion chapter, but I feel like it's good to introduce the idea right now, just to kind of plant the seed. The idea when we're experiencing circular motion is that the object will have its velocity turn around in such a way that all of this initial velocity tilts downward at an angle such that how do I want to word this? Man, I have the idea in my head, but wording it correctly is just a struggle. Let me think. How do I want to say this? Basically, for a tiny enough delta V, the difference between these lengths is going to be negligible. And when we get to circular motion, the other twist is that the direction of the acceleration is not going to be constant. So the direction of delta V is going to be rotating with V initial as you go. I don't know how much sense that's going to make right now, but basically, if you go from this to a split second later, your V initial looks like this, but your acceleration has also changed so that your delta V looks like this. And if you just keep doing that as you go around, so this will cause it to tilt, I guess, towards this direction, and then your next velocity is going to be in this direction, but your next delta V is going to be perpendicular to it in this direction. Then if you keep changing the direction of your acceleration every fraction of a second as the direction of the velocity changes, then you can get away with keeping the magnitude of the velocity constant while its direction is always changing. We will go back to this idea later when we reach the circular motion and gravitation chapter, but for now I want you to just kind of have that idea in the back of your head and maybe reflect on it over the next few weeks. Hopefully that made some semblance of sense, but even if it didn't, just let it sit in your head for a while, and maybe over time your brain will subconsciously start to piece it together. Okay, so back to this classic projectile motion case. I think I'm just going to redraw it over here. What color did I use? I used blue for this. So you have an object, let's say it's launched with V initial is equal to, how about 50 meters per second in terms of magnitude. In terms of direction, I guess I drew the angle too big, but let's say that this is theta equals 30 degrees. And we want to analyze the motion of this object. It's going to go up into the air, hang out for a little while, and come back down to ground level. I'm going to highlight some key points over here. Okay, how do we analyze this motion? What are our equations going to be? Like I said earlier, it's just going to be our classic kinematics equations, but we're going to combine them with our vector decomposition rules. Let me see, we have a question in the chat. Is the acceleration equal to velocity over displacement? No. Acceleration is change in velocity over change in time. Acceleration is a rate of change based on time. Velocity over displacement, I don't know any important physical quantity that's defined by that ratio. Okay, back to, where were we? Right, so the additional twist here is just the vector decomposition. So we have this V initial, and what we would like to do is unpack it into two separate one-dimensional kinematics problems. Because, drawing these vector diagrams for moment to moment is kind of tedious, and there's an easier way. So if I go ahead and break up my V initial was 50 meters per second at an angle of 30 degrees. I can break this into a horizontal component and a vertical component. So horizontal part is going to be this. I'm going to call it Vx initial, since it's the x component of the initial velocity. And I guess I could draw it over here, or, well, I would prefer to draw it over here, but I've already written my 50 over there, so okay, fine. I'll write it over here for now, or draw it, rather. This would be, whoops, Vy initial, the y component of the initial velocity. And if you remember how to do this, then you should remember that this component is opposite to the 30-degree angle, so it's just going to be hypotenuse times sine of the angle, so 50 meters per second times sine of 30 degrees. And this would be the adjacent component. Adjacent goes with cosine. Remember, sine and cosine go with opposite and adjacent respectively, not y and x. A lot of people just tend to assume that sine always gives you y and cosine always gives you x, but you have to ask which side is the angle touching. It's about opposite versus adjacent. Okay, 50 times sine of 30, well, 30 is a special angle, as most of you would know. Sine of 30 is exactly 1/2, so 50 times sine of 30, I get Vy initial is equal to 25 meters per second. And it'll be positive 25 meters per second since it's upward. Okay, what about Vx initial? That's going to be 50 cosine 30. According to my calculator, that's approximately 43.30. So Vx initial is equal to 43.30 meters per second. Okay, and where do we go from here? Well, now we can just do two sets of kinematics equations, one for the x direction and one for the y direction. So for the x direction, I will write Vx final equals Vx initial plus acceleration in x times time. Delta x is equal to Vx initial times t plus 1/2 acceleration in x times t squared, and Vx final squared equals Vx initial squared plus 2 times acceleration in x times delta x. So same kinematics equations that we have learned before. Only thing to note is that we're being very specific about all of our variables involving the x direction here, except for time. Time doesn't really depend on whether you're moving horizontally or vertically. The horizontal and vertical motion are both happening at the same time. You could say they're being tracked by the same stopwatch. So there is no need for a tx versus ty. The time that passes during the horizontal motion occurring is also the same amount of time that passes while the vertical motion is occurring. So you could say tx equals ty equals t if you're stuck on getting past that little detail. Anyway, for the y direction, we're going to do basically the same thing. Vy final equals Vy initial plus acceleration in y times t delta y is equal to Vy initial times t plus 1/2 acceleration in y times t squared, and Vy final squared equals Vy initial squared plus 2 times the acceleration in y times delta y. As long as your acceleration in x and y are constant accelerations, you can use these equations for every scenario and they will work just fine. Now, in the case of projectile motion, 95% of the time your acceleration in x is going to be non-existent. Your acceleration in x will usually be 0. So acceleration in x equals 0, and then in parentheses I'm going to say usually. And the consequence of that is that we can just throw out 2 out of these 6 equations. So first, if the acceleration in x is 0, then we can take that first equation and say Vx final equals Vx initial plus 0 times t, which tells us that Vx final equals Vx initial. Leads us to the conclusion that Vx final equals Vx initial. So if they're going to be the same, if the x component of the velocity is constant, then we might as well just call it Vx without having to specify if it's initial or final or anything in between. So that's the first equation we can throw out. The second equation, we won't throw it out, but we will simplify it. Delta x equals Vx initial times t. Well, now we're just calling it Vx. We don't even need the initial anymore. But I'll write it here for the first time, just for the sake of showing what I'm copying from. Equals 1/2 times 0 times t squared. Okay, that's all gone. This whole thing just goes to 0. And that leaves me with delta x equals Vx initial times t, or just Vx times t. Since again, initial versus final doesn't really make a difference for the x direction. And the third equation is probably even less useful than the first. It tells us Vx final squared equals Vx initial squared plus 2 times the acceleration times delta x. Which just gives us, well, the acceleration is 0. I don't know why I didn't write in the 0 here, but 2 times 0 times delta x is just going to be 0. And you're left with Vx final squared equals Vx initial squared. Which tells us that Vx final equals plus or minus Vx initial, but we already know from the first equation that it's not plus or minus, it's definitely plus. So yeah, this is just, I guess, extra confirmation for what we learned over here. So usually the equations in your x direction will just simplify down to delta x equals Vx times t. And for the majority of your projectile motion problems, it'll be just this equation in the x direction and these 3 equations in the y direction. In the y direction, you have your acceleration y is usually negative g, or some other value if you're, on a different planet. And that's where most of the math is going to happen. Most of the math is going to involve the vertical part of the problem and not the horizontal part. That's where most of the change is happening. Okay, so now that we have all of that laid out, how about we try and do a basic projectile motion problem? Let me see, what question do I want to ask here to get us started off? How about, let's figure out how far has this object traveled horizontally, where is it vertically, and what is the velocity, I'll call it the final velocity, at time, how about we do this at time t equals 3 seconds. Let's ask those 3 questions. For an object launched at a 30-degree angle with an initial speed of 50 meters per second, what is the horizontal displacement, what is the vertical displacement, and what is the final velocity after 3 seconds have passed? So I guess we can go ahead and answer the first one. Should be pretty easy. Delta x is equal to Vx times t is equal to, well, Vx, or Vx initial as I called it earlier while we were decomposing it, is 43.3. And multiply that by 3 seconds, and we get what, 129.9 if I'm not mistaken? Yeah, 129.9 meters equals 129.9 meters. Okay, now we get to the more difficult part. What is delta y? So for delta y, it's only more difficult because there's more terms to throw in, but we already have all the information we need. We have Vy initial, that was positive 25, times t, which is 3, plus 1/2, the acceleration in y is just negative g, negative 9.8, times t squared, times 3 squared. Let's put all that into our calculator and see what we get. 25 times 3, I guess that's going to be minus 4.9 times 3 squared, or times 9. And I'm getting 30.9 meters. 30.9 meters. Okay. So we know this thing is 129.9 meters away from where it was launched horizontally and 30.9 meters from where it was launched vertically. There are going to be 2 places that are at 30.9 meters high. There are going to be 2 places where that happens. And I'm just going to pick random points here. Let's say, for example, here and here. Probably not to scale, but we'll worry about that in future problems. So we've got 2 different places where I could claim this object is. So I guess the bonus question is going to be, is this object in the first half of its motion on its way up, or is it on its way down? How can we figure that out? There are 3 different ways that we can figure this out. One way is to calculate the amount of time it takes to reach the maximum height. We can calculate the amount of time it takes to reach the maximum height, and we can compare the 3 seconds to that. If I reach the maximum height in, say, 2.4 seconds, for example, then at time 3 seconds, I'm already past reaching the maximum height, and that would tell me that I'm on the way down. If the maximum height is reached in like 3.7 seconds, then we would be at a time before reaching the maximum height, and we would know that we're still on the way up. So that's one thing we can do. Another thing we can do is we can calculate how far do you travel horizontally by the time you reach the maximum height. Let's say we figured out that when you reach the maximum height, you will have traveled 70 meters horizontally. Then that would mean 129.9 meters is already past whatever that horizontal halfway point is. Similarly, if I said the horizontal halfway point is, I don't know, 150 meters, then we would see that this is less than that, and we would know that we're on the way up. So, second method is figure out what your horizontal change in position would be once the object reaches its maximum height. The third method, which I think is the most reliable method and is the easiest in most cases, would be to just use the first equation of kinematics in the vertical. Calculate what sign Vy final has, not even what Vy final is, just is it positive or negative? That would be the way to go about it. And we need to calculate Vy final anyway, so we might as well go for it. Vy final meaning at the end of 3 seconds in this case, is equal to Vy initial, which was positive 25, plus acceleration in y plus negative 9.8 times 3. And I think you can easily see negative 9.8 times 3 is almost negative 30. 25 minus almost 30 is most likely going to be a negative quantity, so we know this object is on its way down, so this would actually be our correct location. This is actually where we are on the way back down. Anyway, plug in the numbers and let's see what that velocity actually is. 25 minus 9.8 times 3 is negative 4.4 meters per second. And I guess that gives us Vy final, but the question was asking what is V final. It didn't specify X or Y. That means we're being asked to find the combined two-dimensional velocity at 3 seconds. We are being asked, what is this velocity here? And I guess I didn't really draw it to scale because it should be smaller than this in terms of magnitude. How do I know it's smaller? Because the y component of the initial velocity was 25, and at all points above the initial height, gravity will have taken away some velocity. Sure, it's regaining it on the way back down, but until it comes all the way down to the height it was launched from, it will still not have as much vertical velocity as it did at the start. And the horizontal velocity is unchanged. So if you do your Vx squared plus Vy squared at any point above the initial launch height, because the y component will be smaller, the overall combined velocity will also be smaller. So yeah, V final, its magnitude anyway, is going to be the square root of Vx initial was 43.3, or just Vx in general, 43.3 squared plus Vy, negative 4.4, squared. If I put all that under a square root, what do I get? 43.3 squared plus 4.4 squared. Right, when I square, the negative disappears. And I'm getting 43.52298. I'll just round to 43.52. 43.52 meters per second. Okay, great, that's the magnitude. But I didn't just ask for the final speed. I asked what is the final velocity. So I need both magnitude and direction. So here we go. It's time to use tangent. So I'm going to have, I want to define the angle made with the horizontal direction. I want this angle to be defined. I guess I will call this angle alpha, since I already used theta for the initial angle. I guess I also could have called this theta 1 and this theta 2, but you know, that's personal preference. So let me see, tan of alpha is going to equal the opposite component, which is Vy final, over the adjacent component, which is just Vx, over the adjacent component, which is just Vx. I don't know what I was trying to draw there. So if I do Vy final over Vx, and I guess technically Vy final here is a negative, but I'm just going to use the absolute values and let my illustration decide whether the angle is up or down, which in this case we can clearly see it's down. So if I do inverse tangent of 4.4 over 43.3, I get 5.8 degrees. I get alpha equals 5.8 degrees, and that's below the horizontal direction, below horizontal. So my complete answer, what is V final? It's 43.52 meters per second at an angle of 5.8 degrees below the horizontal direction. All right, so that takes care of a classic problem. Now I'm going to redraw this again to talk about some key features of this particular case. This is a symmetric case for pretty much the same reasons that the symmetric case in free fall exists. We talked about the symmetric case for free fall. Now we're going to talk about the symmetric case for projectiles. It basically relies on the same idea. Whatever your angle theta is, I'm just going to leave it unspecified here, and whatever your V initial is, you're going to have your V final over here is going to be equal in magnitude and not quite opposite in direction. If it was opposite in direction, it would be down and left. Here, only the vertical component of it is opposite in direction. But it'll be the same magnitude, and the angle will be the same amount, except it'll be below horizontal instead of above, and we can see that by just doing the same thing we did when proving the symmetric case for purely vertical motion. We can say Vy final squared equals Vy initial squared plus 2 times the acceleration in y times delta y. If I'm going from start to finish, what's my delta y there? It's 0. It's second height minus first height, right? The next height minus the previous height. That's 0. So this thing is gone, which tells us Vy final squared equals Vy initial squared, which tells us Vy final is the square root of this, which is either plus or minus Vy initial. And we can see that the y component here is going to be pointing downward as opposed to the initial y component, which was pointing upward. So we know, in fact, that it is just minus Vy initial. And we know that Vx is constant, since the acceleration in x is going to be 0 for most of our scenarios. So we can say that V final is going to be the square root of Vx squared plus the square of negative Vy initial, right? Plus Vy final squared, which is negative Vy initial squared. And this is equal to our V initial. This is equal to V initial, which was just the square root of Vx squared plus the positive Vy initial squared. So yeah, V initial and V final, in terms of magnitude, they are equal. In terms of angle, we can see that they're equal because the initial theta, I guess we'll call it theta initial, is just inverse tan of Vy initial over Vx, while theta final, that theta over there, is equal to tan inverse of negative Vy initial over Vx. It's the same thing. The only thing that makes a difference is the negative sign. So I guess if you plugged it in as the negative value that it is in your calculator, you'll get the negative of whatever this angle is. Usually I don't bother with that. Like I said before, when we were calculating the angle in that example we just had, I just take the absolute values of the two components before dividing, and then do inverse tan. And instead of using positives and negatives to indicate below or above horizontal, I just use the words below or above horizontal to determine which way the angle is opening up. But yeah, there you go. So that proves that the final and initial velocities are the same magnitude and opposite vertical direction, though they don't have opposite horizontal direction. Also, the other big thing that we learned from the symmetric case for free fall was that the time to rise equals the time to fall. So let's see if that's still the case here. I mean, it should be, because the time to rise and time to fall are completely dictated by the vertical motion. The time to rise and time to fall are completely dictated by the vertical motion. The horizontal motion has nothing to do with it. There is no horizontal restriction on the amount of time this object is going to be in the air. The object will rise until gravity kills all of its vertical velocity and brings it down to 0, and then will continue to be in the air until gravity brings it back down to the ground, which, assuming the ground is at the same height as it was when the object was initially launched, we'll also have it coming down at the same vertical velocity. So I can just do, let's see, I guess over here at the top, we would say the velocity at the top is not quite zero. The velocity at the top has a y component that's zero. The x component, however, is constant. So over here, we have Vx, but Vy at the top, Vy top or Vy apex, whatever you want to call it, is equal to 0. We can use this same thing to calculate the time to rise. So I can do first equation of kinematics, I guess. Vy top will be my Vy final for this, equals Vy initial plus acceleration in y times t rise. And we can do, let's see, that'll be 0. Vy initial, where was it? Vy initial is just going to be Vy, or sorry, V initial rather, times sine of the angle that it was launched at. So that's just going to be equal to V initial sine of theta. And then that's going to be minus g for the acceleration and then t rise. And we can add gt rise to both sides. Gt rise is equal to v initial sine theta. I guess I don't really need the parentheses around the theta here since it's clear enough without it. But it's not actually a bad idea to put parentheses around your angles when your algebraic expressions are looking messier. It could help you avoid misreading things. And if I solve for t rise, I get t rise equals v initial sine theta over g. And then we could do something similar to calculate the time to fall back down. I guess we can use the second equation here in the vertical. Actually, wait. Oh, yeah, we can, because what I can do is my V final is going to be negative Vy initial in this case. Vy final equals negative Vy initial equals, we're going to start from the top and go to the bottom this time, so we'll start from Vy top, and then that's going to be minus gt fall. Okay, so negative Vy initial equals 0 minus g t fall. The negatives will cancel out, and if I divide by g, I get t fall equals Vy initial over g equals Vy initial is just V initial times sine theta. Okay, so t fall equals t rise. Conclusion, if we combine these two things together, time to rise equals time to fall. For the symmetric case and the symmetric case only, we are going to see a lot of projectile problems where things are not entirely symmetric. For example, you might see an object thrown at an angle off of a building. You might see somebody standing on top of a building and they throw something off the top of the building and it goes up into the air and then it comes down. This is not a symmetric case. This is not a symmetric case. There is symmetry from this point to this point, But past that, you're just going to have to do things the hard way. Just like it was for free fall. It's good to be aware of it. It's a nice way to quickly check your answers at the very least, if nothing else. But don't be too over-reliant on it. Okay, so that pretty much does it for introductions. I guess now I want to go over just kind of an intuitive check of, why does this make sense? Why can we just separate this into a horizontal part and a vertical part and treat them as if they're happening separately? Apart from, what the math has already shown us, what if I'm just not yet intuitively convinced by this? What if I wanted to explain this to somebody who wasn't all that eager to do math? How would I explain that to them? Well, for that, we need to bring a little friend that I bought the other day, and hopefully I have set up my soundboard correctly for this, but let's go ahead and give it a whirl. So here's our little friend, and if I play this correctly, the giant eyeball of physics. There you go, the giant eyeball of physics. I colored it last night. So basically this thing is going to help us kind of understand perspective. So if an object is thrown at an angle like this, if somebody is observing from very far away, if the giant eyeball is sitting really, really far away, we're talking like thousands of meters away, what do they see? They're too far away to tell that there's any motion towards them or away from them. The eyeball doesn't really see that. What the eyeball does see, however, is something going straight up and straight down. As far as the eyeball can tell, the only thing that's happening in this case is free fall. So the eyeball, when it's positioned over here, the only thing the eyeball sees is this followed by this. That's what the eyeball sees when it looks at this situation. So that's if the eyeball is sitting really far away horizontally and observing. What if you had an observer that was far up in the sky in an airplane or a helicopter looking down from above? What if they were looking down at this scenario from above? And I guess I don't really have enough space to show this really well. But yeah, what if, pretend that there's a lot of space here, and pretend that we're thousands of meters in the sky. If we look down, what do we see? We're too far away to tell if the ball is, projectile, I never really specified that this was a ball, but we're too far away to see if this projectile is moving up into the air towards us and then back away from us. It's too far for us to perceive that very clearly. But what we do perceive very clearly is we see something crossing our line of sight this way, and we see it crossing our line of sight at a constant velocity. So what the giant eyeball sees in this perspective is just an object moving like this. So that is kind of intuitively how you can justify separating the horizontal and vertical parts of the motion. If you're looking at it from far away horizontally, all you see is free fall. If you're looking at it from very far away vertically, all you see is just an object moving horizontally, usually at constant velocity. So there you go. We will probably invoke the giant eyeball of physics in the future when talking about things that involve frames of reference, although you could probably get away with not understanding frames of reference all that much in Physics 1, but it's not too difficult of a topic to grasp once we get to the point where we need to discuss it. Anyway, what do I want to do next? Let me see. So we talked about the classic case. We talked about the three different things that acceleration can do for an object, depending on the angle: changes in magnitude, changes in direction, or changes in just one and not the other. We've talked about all that. We talked about, well, I guess I didn't ask the trick question. Because of free fall, we've gotten used to the idea of saying that velocity at the top is 0. Now we have to be more specific. Now we have to say velocity at the top is only 0 for the vertical part of the motion. This object is still moving with a non-zero velocity overall, even at the peak of its motion, because it still has its horizontal part of its velocity. This is going to be important 2 chapters from now when we talk about energy. You may have heard of the concept of kinetic energy, the energy associated with an object's motion. If an object has some velocity, then it has some kinetic energy, and we're going to see the occasional problem where we need to calculate the energy of a projectile at the peak of its trajectory, and a lot of people will forget that this horizontal velocity component exists. So this is kind of your warning to remember this. Also, the other big trick question, although I think I kind of answered it in the beginning, is that at all points throughout this motion, this object is accelerating. Its acceleration is always straight down. Unless we are hit with a problem that tells us otherwise, that will be the assumption. If we need to do away with that assumption, the problem will tell us, or at least will give us a hint that we need to do so. We might get something like an object is being pushed horizontally by the wind while gravity acts on it. Or maybe we're going to have something that's, launched at an angle with rocket propulsion. That would be a source of horizontal acceleration. And if we run into those cases where horizontal acceleration applies, a lot of students tend to panic, but there's really no reason to panic. Just use your kinematics equations as you normally would in one-dimensional kinematics. Just add the acceleration part to these 3 equations and you're good to go. Figure out what your horizontal acceleration is, and it's just a regular kinematics question. There's really no reason to panic. You're just doing kinematics twice. Once for the horizontal, once for the vertical, and usually the horizontal part will be the simple part. Oh, I just remembered. Definitions. There is a term that we need to talk about. It's a pretty simple term. It's called horizontal range. Horizontal range. Horizontal range is the maximum horizontal displacement. My writing is all over the place today. Displacement achieved, or that can be achieved rather, achieved by a projectile. Sometimes we call this delta x max, but you will also see textbooks call this capital R. Either term is used. In the symmetric case, it's pretty easy to see what that would be. You would just draw this. In asymmetric cases, you just measure it from the horizontal position initial to wherever it lands. So that would be over here, delta x max or big R. I'm sure a lot of people will just prefer big R because it's less writing, but to each their own. Everybody's got their preferences, and honestly there are situations where I also prefer the big R, so I'm not going to tell you what to use. It really depends on the situation. I think I default to delta x max unless I know I'm going to write it a lot, in which case I switch to calling it capital R. Okay, anything else? Well, this next thing, it's not official, but when you want to calculate the horizontal range, usually the way to go about that, as you can see, usually the acceleration in x is 0, and there's not really much you can do with x. You've got your horizontal displacement, you've got your vx, and you've got your t. 3 variables. You need to know 2 of them to solve for the third one. And a lot of times you're either going to know delta x and not vx, or you're going to know vx and not delta x. And usually the second variable you're going to want to get is t, and you're probably going to get it using your equations in the y direction, solve for the t using those, and then take that t and plug it in there. But on rare occasion, you might actually get both delta x and vx and be able to solve for t the easy way and then plug that into your y equations. So it can happen, but usually the way to go is going to be calculating t from one of your vertical equations to then take back to your horizontal equation to solve. And then there's the issue of hang time. That's what I was going to get into. Then there's the issue of hang time. We defined hang time for free fall, a total amount of time that an object is in the air. Total time object is hanging in the air, is hanging in the air. T rise plus T fall, the amount of time it takes to rise to the maximum height plus the amount of time it takes to fall from the maximum height to wherever its landing spot is supposed to be. So hang time is often going to be determined, again, using your vertical equations, but sometimes it's going to be determined by your horizontal equations. So I like to do this thing. It's not really official. You likely won't see this in textbooks, and people will think you're crazy if you write this down on your papers, you know, teachers and professors and whatnot. But I like to separate my projectile motion problems into what I like to call horizontally versus vertically restricted or bounded problems. Horizontally versus vertically restricted or bounded problems. I like to use either the term restricted or bounded. Sometimes I'll use one Other times I will use the other. Horizontally versus vertically bounded projectile motion. Basically, is your object in projectile motion until it hits some sort of horizontal boundary or until it hits some sort of vertical boundary? Usually it's going to be vertical. Like over here, this object is in the air until it vertically comes back down and hits the ground. The ground acts as this vertical barrier that says, okay, once you touch me, you can't go any further. The projectile motion stops once you make contact with the ground. That happens after achieving a certain amount of vertical movement. It doesn't matter how far you travel or don't travel horizontally for this. All that matters is when do you hit the ground. That's when the motion stops. So that would be a vertical restriction or boundary on the problem. Other times you might see, for example, I throw an object at an angle and it keeps going until it hits like some sort of wall or building and crashes through a window maybe. In that case, I actually have a predetermined limit to how far I can travel horizontally, and once I've achieved that amount of horizontal travel, the projectile motion stops. So that's what I would call a horizontally restricted problem. Sometimes you don't even need like a physical boundary. Sometimes you just need to, for example, cross a finish line. Maybe, for example, you have an object being thrown above like a net for tennis or volleyball. This is going to be a very poorly drawn net, but something like this. And you just want to score a goal, and scoring a goal happens once you travel a certain amount horizontally, and then you use that to calculate how much time is required to get there, and then you use that time to figure out, okay, am I above the goal or at the net or under the goal, in which case I didn't really score and probably get a penalty, whatever the rules of the game are. So yeah, horizontally versus vertically bounded problems. That's kind of how I mentally try to separate them, but again, not official terminology, so don't write on your test, because this problem is horizontally bounded. Your teacher or professor or whoever is grading your work is going to look at you like you're crazy. Unless they understand what you're doing, in which case they might actually praise you, but I'm not betting on that. Okay, I guess we can spend the rest of our time just doing some example problems then, and that'll be it for our day. I mean, we still have a few things to learn, and I think the best way to learn them is through the problems. One thing that I don't know if I'll get around to showing today, if not today, then we'll do it next week, is problems where you have to solve for the initial velocity. Those can get tricky. I guess with this chapter, really a lot of the issues that students run into is that they're just not used to doing physics calculations. So they get to this chapter where the problem can start from all sorts of different directions. You're not always guaranteed to start with a known initial velocity and angle. Sometimes both of those things are unknown, and you actually have to find them based on other information, and students tend to get lost when that happens. So we will talk about that when we encounter problems of that nature, and we'll talk about how to go about it. But the basic idea is treat the problem, just do everything algebraically as if you already knew this information, and ask yourself, okay, if I had this information, what would I do with it? Well, first I would do sine and cosine to break it into components. Then what would I do? Well, I would use the vertical component to, I don't know, calculate the time to reach the maximum height, because I know velocity vertical at the top in that case is 0, so that's an additional piece of information I can take advantage of. Okay, then what do? Plug that time in to calculate horizontally how far I travel at that point, etc. Ask yourself, what would I do if I did know that information? And usually that takes you to a point where you get something that you can actually solve, and it's kind of like a reverse engineering mindset. We'll talk about it more once we see it. First off, I think I want to start with this book problem. So it says, a student stands at the edge of a cliff and throws a stone horizontally over the edge with a speed of 18 meters per second. The cliff is 50 meters above a flat horizontal beach as shown in the figure, and I'll draw an illustration for that. How long after being released does the stone strike the beach below the cliff, and with what speed and angle of impact does the stone land? Okay, pretty basic question, but that's what I was looking for. So we are standing at the top of a cliff, which is 50 meters high. Height equals 50 meters. Okay. Object is thrown horizontally with a speed of 18 meters per second. So V initial, or V0 if that's what you want to call it, is equal to 18 meters per second, perfectly horizontal. So you could also call this 18 meters per second at 0 degrees with the horizontal if you prefer. And that is all the information we have. How long after being released, so find t, and with what speed and angle of impact. So this thing is going to fall off like that and eventually land on the ground. I guess I could throw in a bonus question. How far will it have traveled horizontally by that time? There's no reason why we can't calculate that. Okay, so usually the way to start a projectile motion problem is to write down your x and y velocity components. Start with components. If you're not sure where to start with components. So Vx is going to be just 18 meters per second because it was thrown horizontally, and Vy initial is going to be 0. There's no vertical part to this initial throw. It was just thrown straight horizontally. Okay, now that I have that figured out, what other information do I have? I know that the acceleration in y is negative 9.8, and that the acceleration in x is 0. That's what we will assume unless we are told otherwise. And I know that delta y is going to be how much? Be careful here. We're going from someplace higher to someplace lower. Final position vertical minus initial position vertical, from height 0 minus height 50. That's negative 50 meters. we will stick to down as being negative as our default unless we have good reason to deviate from that. And we don't know delta x. That's actually a bonus question that I'm going to ask. What is delta x? And then time is a shared variable between both the horizontal and the vertical. And I guess v final for x is known. It's just still going to be 18 meters per second throughout. A vy final, however, is something that we need to figure out. Okay. So is this problem horizontally or vertically bounded? Let's go ahead and use my special terminology here. What is the time going to depend on for this motion? Are we in the air until we hit some sort of boundary vertically or horizontally? In this case, we're in the air until we vertically reach the height of the ground. Once we're at the height of the ground, we can't proceed any further. Horizontally, there's nothing limiting us. So this is a vertically restricted problem, as I like to call it, which means our total time is going to be calculated from the vertical dimension. So I'm going to use my vertical equations. Also, I don't really have a choice but to use my vertical equations because for horizontal, I'm missing both delta x and t. I only have one known value out of 3. I can't really do anything with that. So let's figure out what I want to use. I know delta y, I know acceleration in y, and I know vy initial, and I'm looking for time. Do I have an equation of kinematics that involves those 4 things? That would be my second equation of kinematics. Delta y equals vy initial times t plus 1/2 acceleration in y times t squared. Aren't you glad you listened to me and memorized your kinematics equations? You did memorize your kinematics equations, right? Vy initial was 0, and then 1/2 of negative 9.8 is negative 4.9, and t squared. Okay, the negative there cancels with the negative there. 50 divided by 4.9, and then take the square root. 50 divided by 4.9 is about 10.20408. If I take the square root of that, I get 3.19438. I'm just going to round to 3.194. T equals 3.194 seconds. Okay, that's the first thing they asked us for. The second thing, with what speed and angle of impact does the stone land? With what speed and angle of impact does the stone land? Okay, for the speed, they're talking about the overall speed, so we need to get v final, not vx final, not vy final, but v final, the combined two-dimensional speed. And for that, we need vy final, so let's go ahead and solve for that. I think first equation will help us here, so vy final equals vy initial plus acceleration in y times t. So that's going to be vy final equals, that's a 0, and that's negative 9.8 for the acceleration, and 3.194 for t. Calculator says negative 9.8 times 3.194 is about negative 31.30. Vy final equals negative 31.30 30 meters per second. Am I surprised that it's negative? No. It started off with no vertical velocity and it only went down from there, so the negative makes sense to me. And 30-ish sounds about right if it was falling for about 3 seconds with an acceleration of almost 10 in magnitude. Getting around 30 makes sense to me. So then we can do Pythagorean theorem to figure out V final. Let me switch to another color here. What do I want to use now? How about you? I don't think I've used this at all today, come to think of it. So I can do V final is equal to the square root of Vx squared plus Vy final squared equals square root of 18 squared plus negative 31.30 squared. I can drop the negative because when you square it, it disappears anyway. 18 squared plus 31.3 squared is 1303.69, and if I take the square root of that, I get 36.1066. I'm going to say 36.11. I'm going to say 36.11 meters per second. That's the magnitude. What about the direction? So this is going to be, it's still going to have a horizontal component. It's going to have this whole vertical component to it. And I want to find that angle, the angle made below the horizontal. So opposite would be the vertical component, adjacent would be the horizontal. Opposite over adjacent equals tangent. So opposite, 31.3 over adjacent, 18, is about 1.7388888. And then if I do inverse tangent of that, I get 60.097. I'm going to round that to 60.1 degrees. So that's going to be at 60.1 degrees below horizontal. And there you go. We have answered the questions of the book. Hello, I have a question. What grade math is this? This is physics, high school to college level. This is for AP Physics, which is a college level course that you can take while you're still in high school. As far as the specific math that you need to know for this course, if you're doing the Physics 1 course, you need to know some algebra and geometry and a little bit of basic trigonometry, which you usually learn between grades 9 and 11. And if you are doing the Physics C course, then you will need to learn some calculus along the way, although you can get pretty far with the same math as you need for Physics 1. So hopefully that answers your question. Now moving on to my question, I had the bonus question of what is delta x? Our delta x is going to be just Vx times t with constant velocity. It's just velocity times time. So that's going to be 18 times 3.194 for our time equals about 56-ish, I would guess. 18 times 3.194, 57.492. 57.492 meters. So that would actually also be our horizontal range. Okay, so those are my, oh, and I forgot to circle my answer here. Those would be our answers to the book questions and my bonus question there. So yeah, very basic, classic problem. That one is basically the same, so I think we'll skip it. Oh, okay, it looks like we're already getting one of these problems that I was talking about. So over here, we have a tennis player standing 12.6 meters. We have a tennis player standing 12.6 meters. This might be a little too big for 12.6 meters, but I'd rather err on the side of bigger so that I have more space to write things. A tennis player standing 12.6 meters from the net. I'll try and draw this with some 3D perspective. Hopefully that works. So yeah, there's your net. Hits the ball at 3 degrees above the horizontal. Well, that's too small to illustrate very clearly, so I'm definitely going to draw a bigger angle than 3 degrees so that I actually have space to write stuff around it. To clear the net, the ball must rise at least 0.33 meters. If the ball just clears the net at the apex of its trajectory, how fast was the ball moving when it left the racket? So it must rise 0.33 meters. So I guess the person's hand and the racket, the point that they hit the ball from, is 0.33 meters below the top of the net, which I'm going to draw from there. Okay, so that is 0.33 meters. It needs to rise at least 0.33 meters. Oh my goodness, I think I did draw this too long after all, or maybe I just didn't draw this net high enough. It's okay, we can work with this. I'll just use different colors to try and keep things clear. So the object is essentially launched at a really shallow angle like this and goes into the air. Yeah, I drew this really poorly, but yeah, it's supposed to reach the peak of its trajectory there and then come back down. After that, this looks almost horizontal. It should be more curved. Actually, no, it should reach the peak of its trajectory over here. Okay, I messed up this drawing. This point and this point are supposed to be at the exact same height. But that's okay, we'll just go with this drawing because I don't want to redraw the whole thing. If the ball just clears the net at the apex of its trajectory, how fast was the ball moving when it left the racket? How fast means speed. How fast means find the magnitude of the initial velocity, the initial two-dimensional velocity. That's what we are looking for. We are trying to find v initial, and we were told, I'm not sure how I want to write this in, we are told that this angle over here is 3 degrees. Okay. let's go ahead and see how we want to do this. So this is what I was talking about earlier, where you actually have to calculate the initial speed. So we're going to pretend that we do know the initial speed. What would you do if you did know the initial speed? Well, we would kind of do what we did here. We would start by writing components. So I would say Vx is equal to V initial times cosine of 3 degrees. And I would say Vy initial is equal to V initial times sine of 3 degrees. Okay, I know that I need to achieve a delta y of exactly 0.33. They said that when you reach the apex of your trajectory, you just barely clear the net, and they said clearing the net happens at 0.33 meters above the point where the ball leaves the racket. So I know my delta y has to be positive 0.33, rises up by 0.33 meters. I also know my delta x has to be at that same time 12.6 meters. And this is going to be important. If we are trying to calculate a two-dimensional initial velocity, then we need information from both dimensions. So whatever we have to do to solve this, you can immediately tell just based on that alone that you're going to have to use your horizontal and vertical equations together. That's kind of your hint. It's not immediately obvious until you think about it for a while, but if you're trying to calculate two-dimensional information, you need information from both dimensions. Feels obvious once you state it like that, but the first time you encounter a problem like this, it doesn't occur to you. Okay, so how would I calculate delta y normally? Well, I guess I could use the third equation of kinematics, but I could also use the second. So if I go for the second, I would get delta y equals Vy initial times t, and we can replace Vy initial with this whole thing in a minute, plus 1/2 acceleration in y times t squared. My other option would be Vy final squared equals Vy initial squared plus 2 times the acceleration in y times delta y. I know my delta y is 0.33. I know my acceleration is negative 9.8. I don't know my Vy initial yet. I do know my Vy final is going to be 0 over here. If it's at the apex of its trajectory, then Vy at the top here is 0. Oh, then I guess we don't actually have to. Okay, I guess it's because we are given the angle. We don't need to do it here, but we will have a problem where we need to solve equations from both the horizontal and the vertical together and combine them. But over here, yeah, I guess now that I've written this, this would be the easier way to go about it. So this is going to be 0 squared equals Vy initial squared. So this stuff squared, that's going to be V initial squared sine squared of 3 degrees. And then plus 2ay delta y. So that's going to be 2 times negative 9.8, so minus 19.6, and then 0.33 for delta y. Add 19.6 times 0.33 to both sides. Oh, yeah. Okay, I was expecting this to be a bit more difficult. We will see a more difficult version of this where the initial angle is not given. And that gives me 19.6 times 0.33, whatever that is, equals V initial squared sine squared of 3 degrees for those who are not used to squaring their trig functions, sine squared of 3 is not sine of 9. You don't do 3 times 3. You're not squaring the 3. You are squaring the sine. I know I went over this when we were doing Unit 0, when we were doing like the math stuff, but it doesn't hurt to repeat it, especially for students who haven't gotten that far in their pre-calculus yet. We take sine of 3 and then we square it, and that is sine squared of 3. We write the square after the sine but before the 3, because if we wrote it after the 3 it would be confusing and people would think they have to square the 3 and then take the sine. So yeah, 19.6 times 0.33 is about 6.468, and if I divide by sine squared of 3, so if I divide 6.468, I guess I'll put my calculator up here so you can see what I'm doing, over, and then I'm going to put parentheses, sine of 3, and then close those parentheses and square that whole thing, square all of sine of 3. And that gets me 2361.40068 is equal to v initial squared. And if I take the square root of that, I get 48.59. 48.59. So 48.59 meters per second equals v initial. Is it plus or minus the square root? I'm going to use plus the square root here because we are calculating the magnitude of the velocity, and magnitudes are absolute values. And I see it actually kind of looks dark. I wonder why that is. Is there something off with my lighting? Sorry, I'm checking the screens on OBS for a minute here. I mean, everything else looks readable enough. Maybe I need to buy myself a new lamp, because I don't like the lighting feels a bit yellowish now. More things I need to buy. Yay. I think the number one thing I want to buy is a better document camera, because this is supposed to record in 720p, and based on what I'm seeing in the videos, it doesn't feel like it's that good. But maybe I just need to mess with some settings. I've played with the settings a number of times, so if it's something with the settings, I haven't figured it out yet. I'm probably better off just buying a stronger camera, but we'll see. Everything in its due time. So that was the only question it was asking. How fast was the ball moving when it left the racket? We're done. The other way you could have solved this, the way that you would have to solve this if you didn't know the angle, is you would use this. So you would use delta y equals vy initial times t plus 1/2 ay t squared. So you would do 0.33 equals vy initial was v initial sine of 3. I probably should have made more space for this. Plus 1/2 negative 9.8, so negative 4.9. And then t squared. And then what you could do is you could take your equation in the horizontal direction. Delta x equals vx times t, which gives you 12.6 equals v initial cosine of 3 degrees times t. And what you could do is you could solve this for t. You could do t equals 12.6 over v initial cosine of 3 degrees. And you could then plug this amount in for t over here. And oh, I forgot the t over there. Yeah, and then you could plug this in to t over here and over here. And yeah, if you plug it in to this t squared, then you're going to have to square an already ugly looking fraction. But sometimes that's what you've got to do. So don't judge it just because it looks too hard. Don't take that as an indication that it's necessarily the wrong path. I mean, sometimes it is. I mean, I've looked at things where I feel like the path I'm taking is too complicated mathematically, and that gives me a hunch that maybe I did something wrong. But sometimes you just have to press onward if the math looks messy and you have a lot of like parentheses and distributions to do. Sometimes you just have to press onward and do exactly that, and you'll get an answer. But yeah, when you run into those scenarios, especially on a test, what I would recommend is skip, go back to it later after you've done some easier questions, and maybe some of those questions will actually give you some inspiration on what to do when you come back to this question. That's another benefit of leaving the more complicated questions for later. So that would be the strategy there. If the math looks too messy to be right, maybe it is, or maybe you actually just need to press onward. But either way, maybe prioritize something quicker and easier and pick up the easy points first before coming back to it, so that you're not stressing about all the questions you're not answering while struggling to find an answer to this one. Anyway, I'm not going to complete this here because we are going to get another problem where we actually have to go through all these steps, and I'm waiting on that. That will probably be coming up next time. I don't see us reaching it today, but you never know. Next up, I think this one is... well, actually, I think this one is easy enough. It's basically the example problem that I gave in the beginning. I already filled that side of the sheet. Let's grab a new one. So this one, I guess I will read it first in case anybody wants to do it on their own, but I don't think I'm going to do it. It says an artillery shell is fired with an initial velocity of 300 meters per second at 55 degrees above the horizontal. To clear an avalanche, it explodes on a mountainside 42 seconds after firing. With 300 meters per second, yeah, you probably have enough vertical velocity to be in the air for almost a minute. I can see that being realistic. What are the x and y coordinates of the shell where it explodes relative to its firing point? Yeah, this is basically, you're given initial velocity, you're given the angle, you can easily get the initial velocity components, and you're given time. It's basically the same example problem that I started things off with, just with different numbers. We'll skip that. But you are more than welcome to rewind through this and listen to the problem statement again and do it on your own if you feel that you need more practice with that. Number 29. A brick is thrown upward from the top of a building at an angle of 25 degrees to the horizontal and with an initial speed of 15 meters per second. If the brick is in flight for 3 seconds, how tall is the building? Ooh. Building of unknown height. So building of unknown height, we'll call it H. you've got a brick thrown, well, I guess it should be thrown from this point. Yeah, forget what I did over here. A brick thrown at an angle of 25 degrees. At an angle of 25 degrees with a speed of 15 meters per second. Magnitude of the total two-dimensional velocity is 15 meters per second. Okay, it goes up into the air a little bit, then comes back down. And we are told that it lands after 3 whole seconds. Not a symmetric problem, so unfortunately we cannot calculate time to rise and multiply it by 2. But we can still figure this out. This is actually just a vertical problem if you think about it. The horizontal part of this doesn't really have any bearing on how long you're in the air. This is a vertically restricted problem, so we're just going to be working with the y component here. So we have t equals 3 seconds, and we have, I don't even need to bother calculating Vx, we'll just do Vy initial equals 15 times, it's the vertical component, it's opposite to the 25 degrees, so sine of 25 degrees, which equals, according to my calculator, 15 sine 25 degrees is 6.339, so 6.34. 6.34 meters per second. And yeah, it's positive, it should be upward. Definitely be careful about that, because if this object was thrown at a downward angle, you would have to remember to include the negative sign yourself. I don't think I warned about that before, but now you have been warned. Okay, so we have 3 pieces of information, because we know the third piece is acceleration in y is negative 9.8. So we can solve. I want to find h, which is going to be related to delta y. If I start here and I end here, then overall my y has changed by this much. Delta y is my height at the bottom, which I'll call 0, minus my height at the top, which I will call h, my height final, minus my height initial. So second equation or third equation? The third equation involves Vy final, which I do not have, so second equation might be better for us. We don't have to worry about potential quadratics because we know t. We can just plug it in. So yeah, second equation is probably the way to go. Delta y, which equals, I guess we'll call it equals negative h, is equal to Vy initial times t plus 1/2 ay times t squared. I'm sure many of you are getting annoyed that I write it out almost every time, but I think that's what helps it stick. So negative h is equal to 6.34 times t equals 3, plus 1/2 negative 9.8, so negative 4.9, and 3 squared. And let's see what we get. 6.34 times 3 minus 4.9 times 9. And I get negative 25.08. Negative h equals negative 25.08 meters. The negatives cancel out. H is equal to 25.08 meters. That's about the height of maybe 4 or 5 average height males standing on top of each other's heads. Actually, no, wait. Meters, not feet. So actually about 3... Hold on. What? Let me do this math real quick. So 25.08 meters is approximately 75 feet. Average male is about 5.75 feet. So divide by 5.75. So, okay, 13. That is the height of about 13 average height adult males standing on top of each other's heads. Just for perspective on how tall that building is. Okay. Next we have a place kicker must kick a football from a point 36 meters or about 39 yards from the goal, and the ball must clear the crossbar, which is 3.05 meters high. When kicked, the ball leaves the ground with a velocity of 20 meters per second at an angle of 53 degrees to the horizontal. By how much does the ball clear or fall short of clearing the crossbar? And does the ball approach the crossbar while still rising or while falling? Let's draw it out. So we have a 53-degree angle, so pretty high up. Something like this, 53 degrees. And they said it was kicked at 20 meters per second. And it's 36 meters away from a crossbar. Okay, I guess I drew this pretty poorly, but we'll see. 36 meters away from a football crossbar. For those of you who are not American, this is referring to American football. The crossbar looks like this. It looks like a giant fork. And basically, if the ball goes in between the positions of these two vertical bars, then it counts as what they call a field goal, which is worth I don't know how many points because I'm not that big of a sports person myself. Most of my knowledge of sports comes from these physics problems, actually. Maybe that's not something I should be laughing about. Let's see. They said the crossbar is 3.05 meters high, so let me put that on my illustration over here. So this is 3.05 meters. And what else do they give us? 36 meters from the goal, 3.05 meters in height, 20 meters per second for the initial velocity at 53 degrees to the horizontal. And yeah, that's all. So by how much does the ball clear or fall short of clearing the crossbar? Clearing the crossbar means getting above it, so getting to 3.05 meters high or higher. That would be considered clearing the crossbar. Falling short of clearing means not clearing it, means landing, lower than 3.05 meters. Just in case English isn't your first language and that particular phrasing didn't make much sense to you, that's what they're asking. I would imagine that you could just see the numbers and kind of do some psychology and guess what the writers of the problem want you to do. So maybe non-native speakers won't have that much trouble here as long as they're paying attention to the math. So is this horizontally restricted or vertically restricted? I would say horizontally restricted, because the point in question, we need to figure out at the time that the ball has traveled 36 meters horizontally, where is it vertically? So we need to figure out how much time it takes to achieve its horizontal travel first, and then based on that time, calculate where it is, whether above or below this crossbar. So I'm going to solve for time using my horizontal information, and I actually can do that because I know initial velocity and I know the angle, which means I know the x velocity, and I know the x displacement, so I can solve for the time. Delta x equals vx times t. After all, I can calculate delta x, I can calculate vx, which means I can plug them into this equation to get t. So we've got 20 cosine of 53 will give me my horizontal velocity component, and then 20 sine of 53, I guess I'll draw it off to the side here, will give me my initial vertical velocity. So 20 cosine of 53. Well, you might remember 53 is a special angle. You might remember that 53 is one of the angles in your 3, 4, 5 triangle, or 6, 8, 10 as it were. 4, and then 3, and then 5. That angle is approximately 53 degrees, actually closer to 53.1 if I'm not mistaken. So yeah, I can just say that the cosine is 3/5. 3/5 of 20, so Vx equals V initial cosine of 53 degrees, which is approximately 20 times 0.6, or 12 meters per second. And I think they intended for you to round to 12 meters per second here, because as you can see, delta x, 36 meters, divides easily by 12. It cleanly divides by 12 to give you 3. 36 equals 12 times t, divide by 12, and t equals 3 seconds. Okay, I shouldn't really have circled that because that's not my final answer. But I get in the habit of circling things that are important. That's a habit that I need to try and get rid of. I mean, if I was doing a test, I wouldn't do it. I'd be much more careful about it during a test. But when I'm teaching, I don't know. I just feel like it's important to put emphasis on important information, so that's kind of why I do it, for better or for worse. Anyway, I can just use the second equation of kinematics. Now that I know t, it should be easy enough to use. Equals Vy initial times t plus 1/2 acceleration in y t squared. Delta y, we don't know yet. That's what we're solving for. Equals Vy initial. Vy initial is going to be V initial. V initial. I messed that up big time. V initial times sine of 53 degrees. Sine of 53 degrees is 4/5, or 0.8. 0.8 times 20. 20 times 0.8 equals 16 meters per second. So 16 times 3, And then 1/2 of negative 9.8, that's minus 4.9. And then times 3 squared. So 48 minus 4.9 times 9. 48 minus 4.9 times 9 is 3.9 on the dot. Is exactly 3.9 meters. But that is not what we were being asked. The question was, by how much does the ball clear or fall short of clearing the crossbar? By how much? If delta y is 3.9, 3.9 meters, then what they are asking us for is this difference. That's what they're asking for. 3.9 minus 3.05. 3.9 minus 3.05 equals 0.85 meters. So we say clears by 0.85 meters. If it fell short, same thing. You wouldn't say negative 0.85. You would just say falls short by 0.85 or whatever the number happens to be if it was less than 3.05. Okay, and then part B, does the ball approach the crossbar while still rising or while falling? I guess it's a good thing that I didn't draw a trajectory yet. If I had to guess, it would be on its way back down, because that's usually how people try to kick balls. They try to kick them in such a way that they land towards their target, not going through their target on the way up. But we already talked about how to do the math for this, so I would just, the easiest route would be to just calculate Vy final. Vy final equals Vy initial, which was 16, plus acceleration times time, so that's negative 9.8 times 3. And I think you can already see this is almost negative 30 versus 16. This is going to be negative. What's important is that it's less than 0. It doesn't matter what the exact number is. So on the way down, So the actual trajectory looks like something like this. And not, I guess I'll do this in red, it is not this, right? It's not still on its way up when it crosses the crossbar. So I'm just going to X that out to emphasize that it's the wrong trajectory. Okay. What do we have next? A fireman, 50 meters away from a burning building, directs a stream of water from a ground-level fire hose at an angle of 30 degrees above the horizontal. If the speed of the stream as it leaves the hose is 40 meters per second, at what height will the stream of water strike the building? I think I might be able to fit that on this page. So a fireman 50 meters away from a burning building. I don't know why I made it that big. 50 meters away from a burning building. Directs a stream of water from a ground level fire hose at an angle of 30 degrees above the horizontal if the speed of the stream as it leaves the hose is 40 meters per second. At what height will the stream of water strike the building? So 30-degree angle. Let me do this in, let's do purple. So at 30 degrees, and they said it was a speed of V initial equals 40 meters per second. And if it were to continue, I guess it would do something like that. I'm guessing here that it's on the way up. It could very well be that it goes, up and then comes back down on the building. So we will find out after we do the math whether or not it'll be rising or falling when it hits the building. But anyway, if the speed of the stream as it leaves the hose is 40 meters per second, at what height will the stream of water strike the building? That is the question. At what height will the stream of water strike the building? I guess the way I drew this trajectory, it makes it look like it goes straight, which is bad drawing on my part. But yeah, the path is supposed to curve. Anyway. Anything else I need to gather from the problem statement? No, I've copied all the numbers. Okay, then let's get calculating. So Vx and Vy initial, I'm gonna need both here. I have, in this case, this is what I would consider a horizontally restricted problem. The water is in the air until it travels 50 meters horizontally, and that's when the projectile motion stops. So Vx is going to be 40 times cosine of 30 degrees, right? Vx is going to be this component, which touches the 30-degree angle. Adjacent goes with cosine, and then Vy initial is going to be this, which, if you copied it over from here, is opposite to the 30-degree angle. So 40 cosine of 30 degrees, and then Vy initial is 40 sine of 30 degrees. Sine of 30 I can do without my calculator. Sine of 30 is just 1/2, and 1/2 of 40 equals 20 meters per second. Calculator for Vx. Hey there, quick question. Will there be a lesson live talking about angular motion? Yes, if you click in the description, you're going to see the entire course plan. That's going to be, what was it, the third to last chapter, I believe. It's somewhere towards the bottom. It's going to be rotational kinematics or rotational dynamics, I think. It's under one of those two. I forget what I called it. But yeah, that will be coming in the future, but we're still about a third of the way into the course at this point, so it'll be a while before we get there. Okay, where was I? Right, calculate Vx. So that's going to be 40 cosine of 30 degrees, and I get 34.64. All right, much appreciated. You are welcome. But definitely make sure to do your own studying, because I don't think videos and live streams alone are going to cut it if you don't do your own work in between. Seeing me just once a week is probably not going to be enough. You'll just have to trust my experience on that. 34.64 meters per second. Okay. So this problem is, again, going to be horizontally restricted. That is, my time depends on how soon I arrive at a certain horizontal threshold. So let's calculate that first. We can do, let me switch colors here. We can do delta x, which is 50, equals Vx times t. 50 meters equals 34.64 times t. So we can solve for t. Hello, Anya. If you have questions relevant to what we are doing, feel free to ask. If it's something that's not immediately answerable, I will postpone it until the end. Anyway, 50 over 34.64, I'm getting about 1.443 for the time. T equals 1.443 seconds. Now that we have that, we can calculate h pretty easily, because it's just going to be equal to my delta y. And to calculate my delta y, I don't know why I did this from right to left. I guess for the sake of making sure I had enough space. Delta y, I can just use the second equation of kinematics. The third equation is not getting a lot of love today. Delta y equals Vy initial, which is 20, times t, which is 1.443, plus 1/2 acceleration times squared. 1/2 of negative 9.8 is negative 4.9, and 1.443 squared. Plug all that into the calculator. 20 times 1.443 minus 4.9 times 1.443 squared. I'm getting 18.6569. I'll say 18.66. I'll say about 18.66 meters. That should be a good enough number of decimals. And I'll just circle that as my final answer. So I'll just put h equals there, and now I don't have to write anything more. Okay. We are 2.5 hours in. I think, well, I guess we can answer one more thing about this. This wasn't really asked by the problem, but might as well do the math. So if time is 1.44 seconds, I'll say 1.5 seconds. 1.5 times negative 9.8 is about negative 14.7, and Vy initial is 20. So if you lose about 14.7 or less, you still have a positive velocity. So yeah, this water is going to hit the building while still on the way up. So my original illustration is still pretty accurate, minus the part that this looks too straight. Anyway, I think I want to pick our last problem for the day and then talk about what I would recommend doing for homework. And I guess next time that just leaves a lot of the really advanced projectile problems. So yeah, like I said at the beginning, not a lot of new stuff for us to learn in this chapter. We're just combining the stuff that we learned from the previous chapters. That's why we were able to blow through this so quickly. We're already pretty much halfway through. So next week we might be wrapping this chapter up, in all likelihood. Anyway, what do I want to go with? I think I'm going to leave that for people to think about at the end. What about this one? A projectile is launched with an initial speed of 60 meters per second at an angle of 30 degrees above horizontal, lands on a hillside. 4 seconds later. So far looks like a very basic problem. Oh, okay. That second question is something different. Okay, let's do this one. I mean, the beginning is pretty simple, but the end is, well, still simple, but different, so still worth looking at. Let's see. So it says a projectile is launched with initial speed 60 meters per second at an angle of 30 degrees above horizontal. Okay, 60 meters per second for V initial. The projectile lands on a hillside 4 seconds later. 4 seconds is, let me do some quick mental math here and see if it's going to be on the way up or down. You don't have to do this, but I want to do it so that my drawing is accurate. So it would be, okay, yeah, that would be on the way down. We can show the math for that later, if need be. Okay, so like somewhere here, I guess, would be when it lands on a hillside. And I guess I'll draw my hill like this. Okay. 60 meters per second, 30 degrees above horizontal. Time is 4 seconds. And the questions are, what is the projectile's velocity at the highest point of its trajectory? What is the velocity here? I guess that kind of gives away that it lands on the hill on its way down. Otherwise, it wouldn't have reached its highest point in trajectory. And then part B, what is the straight line distance from where the projectile was launched to where it hits its target? So what is, did I draw that correctly? I probably should have brought out a ruler for this. Actually, I think I got it pretty much without the ruler. Yeah, what is this? What is this distance? Is the second question. So what is V over here? That's the first question. And what is that distance? And orange was probably not the right color to be using here. The lighting looks really bad. What is wrong today? It's never been this bad. Well, I'll figure out the lighting situation for next time, definitely. Let's see. Anything else I need to get from this problem statement? Doesn't look like it. Okay, we're good to go. So, color. What do I want to use? I guess I'll use this one. So, let's start off the same way we usually do with our velocity components. So I'm going to get Vy initial, which is going to be 60 times sine of 30, so that's Vy initial, and Vx initial, or just Vx, is gonna be 60 cosine 30, so 60 sine of 30. Sine of 30 is exactly 1/2, so that's going to be 30 meters per second. And then Vx 60 cosine of 30 degrees is going to be 60 cosine 30 is going to be 51.96 approximately. 51.96 meters per second. And we can calculate, first of all, what is the velocity at the peak of the trajectory? We already have it, 51.96, right? At the peak of the trajectory, we said the y velocity is 0, the x velocity is all that there is, and the x velocity is 51.96. So that part is a very quick answer if you know what you're doing. Very quick answer. This would be like a 10-second multiple choice question. You could do this really quickly if you have your wits about you, and if you've practiced enough with these problems. Okay, the second question is, what is this distance? So that's the more interesting part. To calculate this distance, what we would need to do is, let me switch colors for this. What we would need to do is just draw a right triangle. So you would figure out what this is, and then figure out what this is. Figure out your delta x and your delta y. And by definition, they're perpendicular to each other, and you've made a right triangle, and the rest is just Pythagorean theorem from there. So let's figure out delta x and delta y. Delta x is going to be the easier one, so let's do that first. Pick up that partial credit, if we were pretending this was a test. Delta x is Vx times t equals 51.96 times 4 seconds equals a little over 200. 51.96 times 4, 207.84. Never hurts to try and estimate what your numbers are going to be before you put them into your calculator. That helps you catch any mistakes if you get a number that feels way off. And delta y, I'm going to use second equation. So that's going to be Vy initial times t plus 1/2 acceleration in y times t squared equals 30 times 4. 1/2 times negative 9.8 is negative 4.9, and then times 4 squared, or 16. 120 minus almost 80. So I'm getting something close to 40, a little bit more. 30 times 4 minus 4.9 times 16 is 41.6. 41.6 meters, so 41.6 here, and 207.84 there. By the way, this is something you're going to notice a lot with projectile motion. A lot of times the horizontal distance traveled is going to tend to be greater than the vertical distance traveled, or displacement rather. And there's a simple reason for that. In the horizontal, all you ever do is just increase in displacement until, of course, the projectile motion stops. In the vertical, there's going to be some sort of maximum height. You're limited in how high you can go, and after enough time has passed, you start coming back down. So yeah, it will often be the case that delta x is larger than delta y, but not always. Because if you fire at a high enough angle, then you might get something like this, where your maximum delta y is way bigger than your maximum delta x. But for shallower angles, don't be too surprised if delta x is way bigger than delta y. Anyway, I can just do Pythagorean theorem here, so 207.84 squared plus 41.6 squared, and then take the square root of that ridiculously huge number, and I'm getting 211.96. It is greater than both of these, so I believe it. D equals 211.96 meters. All right. That will be our last problem for the day. So, what I would recommend doing for homework. I'm gonna do what I do with a lot of these streams and end you off with a somewhat challenging problem, which we will address at the beginning next time. But also, let me see, is there anything in particular from the course plan that I want you guys to look at? Let me switch screens here. So yeah, if we go to projectile motion, we've got, I already told you guys to look at those items. And yeah, this third item is the one that I said I would add last week. So hopefully you guys went back to look at it after I added it. Wait a minute. Oh, I didn't link the simulation in here. Okay, that's something I'm going to need to modify. I mean, the video that this links to will show you the simulation anyway, but yeah. Worked examples, so go to, that will take you to Michel Van Biesen's channel, where he does a lot of example problems. So definitely look at problems from him. You might even see some of the more difficult problems that I plan on doing next time if you go there. And other than that, if you haven't done so already, we've already covered everything that's needed, so you should be able to do all of the conceptual questions and the problems and exercises from the book. And if you don't have the book, it is linked up here. You can download it for free. It looks like this. And yeah, just go to, what is it, chapter 3, and skip over to the conceptual questions, problems, and exercises, and try out a few until you feel that you've got a good grasp of how to do everything, and you've got, like, you know, the kind of, until you've developed kind of a sense of direction for how to do these problems. And next time we will be doing some of the more challenging problems. Let me switch back to the camera and talk about our next problem that we will start things off with next time. So it says, and this is what I will send you off with, it says, a soccer player kicks a rock horizontally off a 40-meter high cliff into a pool of water. If the player hears the sound of the splash 3 seconds later, what was the initial speed given to the rock? Assume the speed of sound in air to be 343 meters per second. So, a person standing on a cliff above water. So you've got 40-meter high cliff. You've got a soccer player who kicks a rock and kicks it horizontally. We don't know how fast, but V initial is completely horizontal. The rock lands in the water and makes a splashing sound. The splashing sound is heard, so the sound, we can pretend that it travels in a straight line. Actually, the way sound works is it starts from the center and kind of expands as a sort of growing sphere. But yeah, this person's part of that sphere pretty much travels outward towards him from the center of where the sound comes from. So it's basically fair to treat it as if it travels in a straight line. And they said that the player hears the sound of the splash 3 seconds later. T equals 3 seconds. This is the total time, which is probably giving away too much information. That's the total time. You need to split this into 2 phases. The amount of time it takes for the rock to land in the water, and then the amount of time it takes for the sound to come back after that. So that's one of the major twists in this problem. And then the other thing they give us is V sound, which you can treat as a constant velocity, is equal to 343 meters per second. So think about that, see if you can figure it out, and if not, don't worry, we will start off with this one next time, and a couple of other moderate to difficult projectile problems is what I have planned. So yeah, I guess that'll be it. In terms of traditional office hours, I think I'm just going to move that to a different day. I'm probably going to do that tomorrow instead of doing the 15-minute break and then coming back to it. So yeah, if you're waiting for traditional office hours, that's probably going to be tomorrow. I'm thinking of just going over a couple of calculus techniques to follow up on what I did, what was it, like 2 weeks ago with Riemann sums, because I feel like I need to cover a wider variety of functions before we can do some of the other Riemann sums that I'd like to show off. And I also bought some new toys to help kind of illustrate those ideas. But yeah, those are for like the AP Physics C students. You guys might be more interested in that since it'll teach you some calculus. Anyway, that's enough rambling from me. Take care, do your homework, enjoy what little remains of your weekend. Some of you are probably in other countries where it's already Monday. And take care, and I will see you next week.